Okay, so we're to the final session of IEEE VR 2022. This is the advanced UI session. And our first author is Guillermo Bernal from the MIT Media Lab. He is going to be presenting Galea, a psychological sensing system or physiological sensing system for behavioral research and virtual environments.
Great, thank you. I will begin sharing. So, 1 second. Can you see my screen?
Yes.
Great. Hello, everyone. And my name is Guillermo Bernal. Thank you for joining us for this presentation. I'm presenting this paper also in collaboration with Nelson Hidalgo, Conor Russomanno, and Pattie Maes. We are excited to share some of the work, and I'll be trying to answer the questions afterwards if you have any. So as we know, virtual reality offers great promise as an intervention modality for researchers interested in studying human behavior because it can provide an accessible, controllable, replicable, and safe environment to do human subject environments. While understanding a single physiological signal can be insightful, it is even more useful to be able to examine multiple modalities. So to understand human behavior and to in the individual responses to the environment and the gain insight into their cognitive process. However, conducting this type of research does not come without challenges. For example, accessing the equipment for recording data from the user, synchronizing physiological response data with a stimuli or interactive environment is not a trivial task, and generating virtual content in response to the user's real-time data, it can be costly and complex. We have developed Galea, a device for multimodal signal acquisition able to measure the physiological response of the user when experiencing virtual content, enabling behavioral affective computing and human-computer interaction research and applications to access data from the allowing us to access data from the parasympathetic nervous system and sympathetic nervous system simultaneously. In recent years, research in human-computer interaction has explored how to integrate physiological computing into everyday life. Early work by Masai et al. Is exploring adding sensing actuators to eyewear to collect physiological deformation. Bernal et al. Developed a system to express emotional avatars using using electrodermal activity and heart rate in virtual environments. And the Physio HMD project kind of took that work further, allowing it for this type of sensing in different modalities to be easily accessed into different type of headsets, while also being able to explore other APIs like voice and as well as movement. Outside of the human-computer interaction and adding capabilities, a lot of these physiological measures are often used to calculate or evaluate users' underlying cognitive process in virtual environments. Amore's amazing psychic VR system integrates the Muse, a consumer PCI headband with VR headset to teach mindfulness while enjoying playful experience. Gupta et al. Measurement of attention and mental workload using physiological sensors show how this approach can enable researchers to measure and understand human trust in virtual agents using the metrics like cognitive load and agent accuracy in order to interact or understand trust formation between virtual agents and users. Also, Fowler et al. In their custom VR closed loop system have shown that neurofeedback can be used to downregulate arousal to improve human performance in demanding sensory motor tasks in real time. Also, more recently, Luxit Labs, Neurable, and MTech VR have come out with unimodal solutions for commercialization. The Luxit Labs products reads brain signals from the prefrontal cortex region in order to assess the user's attention and relaxation. Neurable limited unit run was used to collect signals from the occipital region in order to use it as a mechanism of interaction. And MTech VR uses the facial muscle signals to understand the user's facial expression. Each one of these products looks at one specific physiological signal, which provides insight into one domain, but does not result in a novel research tool that allows researchers to examine how individual signals may work together or impact each other at a specific cognitive processes. In order to understand more complex human behavior processes, it is important to be able to monitor multiple signals, as it is impossible to with the system presented in this publication. Why do we care about this? Because our cognitive process in our behavior is influenced by two modalities. We have our somatic nervous system, as well as our autonomic nervous system, our flight and flight response, as well as like rest and digest, that allows us to have these different modalities to interact and contribute in how we engage into a lot of the processes or a lot of tasks in our day-to-day life. So we want to be able to analyze, to understand a more complex signals by being able to tap into this different modality. In our case with Galea, we can begin to look into things like attention assessment, being able to look into cognitive flexibility, use it for neurorehabilitation, to understand more facial expressions, so we can provide better understanding how people are responding to content, as well as to look at other things like stress management. And how do we do this? We develop a pipeline that begins to transmit all these packages that are being generated by our system, that are rich in data over Wi-Fi, and being able to look at all these data in real time through a GUI that allows you to understand the quality of your signal, how you process that signal, all compatible with lab streaming layer, a protocol that you will find in any neuroscience lab, and as well with Python libraries that then can all be included into a game engine that will allow the researcher, in order to be able to time lock any stimuli that you're trying to understand. When something happens, you present an event, a marker into your data collection pipeline for online or offline. This is some of the how you would normally put and will expedite how this type of research will happen in real time. Trying to do this research with current system can take up to 15 to 30 minutes when you begin to do wet caps and all the type of sensing. For us, we can do it in a much shorter way. I'm running out of time, so just kind of going to go through this much quicker. Here, this is kind of the different modalities of the signal that I have mentioned before. The FacePass has like the different sensing capabilities, and in the back there is like data for the occipital. As part of our paper, we wanted to do this paper almost as a tutorial, where we kind of show you how each one of the signals look, what's the quality of the signal. When you're doing physiological signal, it's very important to understand how much data is the resolution of the signal being collected. So we present different metrics in order to see how our system compares to others. In looking into like different BCI paradigms, we picked SSVEP as is one of the most popular paradigms, as well allows us to look further into a very small signals, which is steady state evoked potentials, in order for us to be able to say like our system is providing very good signals. So we look into developing a maze system that looks at SSVEP, providing different frequencies to the user. This flickering are then picked up by the occipital electrodes, the electrodes placed in the occipital region. On the right, you can see like the different frequencies that are being picked up by the system. We run a study with 6 participants to understand how a canonical correlation algorithm would do with our signals, how it compares with others as well. Many times we actually meet or exceed existing systems. So with our paper, we provide now a extremely rich environment for researchers that want to use BCIs and virtual reality to conduct behavioral studies. Thank you.
Great, thank you, Guillermo. All right, so our next speaker is Shakiba Davari from Virginia Tech. she'll be presenting validating the benefits of Glanceable and context-aware augmented reality for everyday information access tasks.
Okay, thank you. Hi, I'm Shakiba from the Center for Human-Computer Interaction at Virginia Tech, and today I'm happy to present our work on context-aware AR. So in today's life, we all rely on digital information, and I think all of us use our mobile phones for a quick information access. But mobile phones have their own limitations, and they occupy users' hand, or their screen size limitations can cause inefficiency or distraction for the user. As an alternative, there's also the notion of glanceable augmented reality interfaces that can potentially use the whole world as their screen, and then they can offer a solution to many of these limitations that mobile phones have. But still, glanceable AR interfaces that have their own challenges. They can create visual clutter, or they can affect user safety and their awareness of their environment by causing occlusion and distraction, like this video. They can also create socially awkward situations sometimes, like this video.
Cool, so guess what? The funniest thing happened. Are you paying attention to me? I can't tell.
So having enough knowledge of the user's context, of who the user is, what their environment and their task is, can provide enough information to know the user's needs and their wants and their limitations, which enables adapting the AR interface to provide the best information at the best time and in the best form for the user, and efficiently presenting that information without causing new challenges for them. As you can see in this figure, when in a conversation, the virtual content must be transparent if they're not needed. And even when they're required, like the weather application here, they can become available automatically, but they still shouldn't block the conversation partner's face. So for this study we conducted, we designed a context-aware glanceable AR interface for two common everyday contexts, a static solo context and a dynamic social one. And for the sake of time today, I would focus on the social context. For more information on the solo context, I invite you to take a look at our paper using this QR code. So for the interface in the social context, we had three design considerations that were aiming to both resolve the existing challenges of glanceable AR and improving information access efficiency. So once our interface detects a social conversation, it prioritizes the real world. It always ensures the visibility of conversation partner's face, and it automatically provides access to socially relevant content. We conducted a within subject user study on 36 participants to study three different interfaces: mobile phone, non-adaptive glanceable AR, and context-aware AR. And in the study, the user's primary task was to engage in a conversation with me. So we aim to simulate a situation where you're having a conversation and a question pops into your head, urging you to, let's say, check the weather. And in the study, we called these questions self-triggered questions. And to simulate them, we played a question through a speaker and then asked the users to use their interface and answer them. And the users were also asked to answer conversation-triggered questions, which was me asking them some questions as part of the conversation. For example, hey, by the way, how's the weather on Sunday? And to measure users' awareness of their environment and their conversation partners' facial expressions, they were also asked to raise their hand every time I winked at them. So in this video, you will see the exercise app would get activated when the conversation topic switches to walking and exercise, which facilitates access to socially relevant information and answering the conversation-triggered question. I love walking, and usually in the cold weather, I can't walk a lot. How about you actually? Do you like walking? Like, how many steps have you walked so far today?
Yeah, I like walking, and today I've walked 2883 steps.
So we had both subjective and objective measures to evaluate information access efficiency, intrusiveness to the primary task and conversation, and user experience and preference. In terms of information access, our results showed that mobile phone was the slowest and the most difficult for information access. And the context-aware interface was the fastest for accessing socially relevant information or conversation-triggered questions. In terms of intrusiveness, mobile phone increased the time away from the conversation, and context-aware reduced it when answering conversation-triggered questions. And context-aware also reduced the number of missed winks. 72% of our participants ranked mobile phone as the most difficult to resume conversation after information access. And they said that it was perceived as the most socially intrusive, while 67% of them ranked the context-aware as the easiest to resume conversation after information access. And the context-aware system was ranked the most preferred by 64% of the participants, and mobile phone was ranked the least preferred by 64% of participants, and it had the least score in most of the UX aspects. Overall, our results shows the disadvantages of mobile phones and the advantages of context-aware AR for information access efficiency, for avoiding negative effects on the primary task and social conversation, and for on overall user experience, showing that an intelligent, adaptive, context-aware Glanceable AR interface can offer more efficient information access alternative to current mobile phones without creating new challenges. Thanks for listening. I'd be happy to answer any questions after the presentations, and if the time didn't allow, please feel free to contact me.
Excellent. Thank you very much. All right, so our next speaker is Jay Lee from the University of Illinois. He will be presenting user preference for navigation instructions and mixed reality.
Can you see my screen?
Yes.
Hi, so I'm Jaewook, and today I will be presenting our work on how different contexts affect user preferences for navigation designs in mixed reality. This work was done in collaboration with Fanjie, Younsoo Kim, and David Lindlbauer. Today, conventional navigation systems are mostly limited to 2D maps on smartphones and voice-based feedback. On the other hand, mixed reality holds the promise of integrating navigation instructions directly in the user's visual field, potentially making them less obtrusive and more expressive. MR navigation systems today are also somewhat limited in that most of them rely on conventional designs such as arrows. Users may prefer different navigation designs beyond just simple arrows, especially under different contexts. Therefore, we conducted a study to evaluate a set of navigation instructions and the impact of different contexts on user preference. To achieve this, we conducted 2 user studies. First, we conducted a crowdsourced study using images to understand user preferences across a wide range of navigation designs and contexts. Then, we took the 4 highest rated designs and ran a virtual reality study to understand if results can be replicated in a 3D environment. Our findings suggest that while arrows are a universally accepted solution, other designs such as avatars, callouts, and desaturations are good alternatives depending on context. So in study 1, we prepared 10 different navigation designs used across prior works and commercial products. The navigation designs are arrows, avatars, callouts, change texture, checkpoints, desaturation, duplicate physical objects, glowing path, saturation, and virtual street signs. We ran an online study on XR-DRN with 50 participants using images to understand user preferences towards a wide variety of navigation designs. In addition to the 10 navigation designs, we varied 3 contexts. First, we varied environment, which consists of outdoor, large indoor, and small indoor environments. Second, we varied time, which consists of not rushed and rushed. This factor depends on the amount of time left until a person has to reach their destination. Third, we varied task, which consists of targeted and browsing. A targeted task means that a person has a specific destination in mind, while a browsing task means that a person is just looking around. We presented participants with 12 different scenarios, each consisting of different combinations of these 3 contexts. So here's an example scenario. You have a reservation at a popular local restaurant. You begin walking towards the restaurant with plenty of time left until the reserved time. This scenario takes place in an outdoor environment. A person is not rushed and is performing a targeted task. Participants were provided with example images to assist with picturing the scenario and the navigation designs. To analyze the data, we used repeated measures ANOVAs with Greenhouse geyser adjustment and Bonferroni correction. So to plot the graphs, we calculated the average points after converting the design's rankings to points. When varying the environment, participants preferred avatars in an outdoor environment over a small indoor environment. Additionally, participants preferred callouts in an outdoor environment over a large indoor environment. When varying time, participants preferred desaturation and rush scenarios over not rush scenarios. When varying task, participants preferred arrows for targeted tasks over browsing tasks. Overall, participants preferred arrows, avatars, callouts, and desaturation designs the most. So then in study 2, we compared the top choices from the first study in a virtual reality environment to see if the preference results are replicated in a 3D environment. First design is arrows. As shown in this clip, the arrows design consists of an array of consecutive sky blue colored arrows placed on the ground. Second is an avatar, which consists of a humanoid figure resembling a tour guide that says, "Follow me." Third design is callouts, which consists of informational displays that shows directions and distances to intermediate goals. Lastly, the fourth design is desaturation, which consists of a grayscale filter that removes color from the world except for the path and the destination. In this study, we only varied the environment. The outdoor environment was a city, the large indoor environment was a museum, and the small indoor environment was a supermarket. Participants were able to navigate each environment using a basic teleportation locomotion. Additionally, arrows were used as baseline because not only was it the highest rated design in our previous study, but it is also a popular MR navigation design amongst researchers and product developers. Participants completed 2 navigation tasks per environment, once with arrows and another with one of 3 other designs. The same analysis steps from study 1 was used to analyze the preference data, but this time it was a 3 environment by 4 visualization type repeated measure ANOVA. The results indicate that the only difference between the arrows and desaturation was significant. In study 1, arrows was rated the highest, then callouts, then desaturation, then avatar. However, in study 2, arrows was rated the highest, then avatar, then callouts, then desaturation. From the 2 user studies, we concluded that arrows are universal. They fit many situations regardless of context. An avatar works well for browsing tasks because it can act like a tour guide. However, it does not work well in a small indoor environment because of its vertical nature, which makes it vulnerable to occlusion. Callouts work best in browsing tasks because it provides additional information and serves as checkpoints. Desaturation works best in targeted tasks because it can effectively shift a person's attention towards the destination. There are several design recommendations to be made about MR navigation designs. First, arrows are universal. However, it can still be improved. A greater sense of companionship is needed for browsing tasks. This was achieved well by the avatars design. Navigation design should include additional information beyond just directions, similar to avatars and callouts. Rush does afford drastic changes. If there is a clear target that a person needs to reach quickly, drastic changes such as desaturation can be beneficial. Otherwise, drastic alterations should not be performed. In conclusion, context plays a significant role in user preferences towards MR navigation designs. Using the results from the study, future research should explore designing automated approaches for context-aware MR navigation systems. Thank you for listening to this presentation.
Excellent. Thank you, Jay. All right, so our next speaker is Lila Bozgeyikli from the University of Arizona. She'll be presenting Tangiball, foot-enabled embodied tangible interaction with a ball in virtual reality.
Thank you. Can you see my shared screen?
Yes.
Thank you. Hi, everyone. So in this study, we explored foot-enabled tangible interaction in virtual reality. In our study, users interacted with a spherical physical ball. And in our experimental technique, which was tangible ball interaction, it included a custom design. We used a two-piece transparent acrylic spheres with a diameter of 6 inches. And we used a 3D printed custom attachment to mount a motion tracker on each face. And as you can see here in the middle picture, the forms of the virtual representation and the physical ball matched one-to-one. And we also used a non-slippery pad that was attached to the ground to make it easier for the user to make the tangible ball come to rest on the start area a bit easier. Our control condition included purely virtual interaction where there was no tangible user interface and participants engaged in purely virtual interaction. And we matched the physical behavior of the virtual ball with the physical ball. So we adjusted the virtual parameters of physics so that the physics of the virtual and the physical balls were as similar as possible. And we adjusted the parameters in the Unity game engine to achieve that, such as weight, drag, and physics materials for dynamic and static friction. To evaluate our design, we came up with a room scale VR game. The dimensions of the physical room were approximately 3 by 3 meters. And the user's goal in the game was to kick the ball once with their foot, aiming to make it come to a rest on the target area. Since it was room scale VR, we used real walking locomotion, and we displayed the ball's distance to the center of the target area in real time to the users, as you can see in the pictures here. We used 3-tiered scoring, indicated by those 3 different colored rings that are seen in the picture. So the start area was fixed for each trial, and we wanted to come up with a self-sustainable game without the help of any outside user. To achieve that inside the game, the user was instructed to bring the ball back to the start area by rolling with their foot, similar to how they interacted with it in the game. And once the ball was on the start area, then a new target was displayed at a random position within a predefined range. And the purple area here indicates that predefined range. So the centers of the target areas were on this purple area. At the beginning of the experimental game, instructions were displayed to the user, and then the tutorial was started. In the tutorial, the user's goal was to repeat the task of shooting the ball, aiming to make it come to a stop inside one of the 3 circles, and then bring the ball back to the start area and repeat it for 3 minutes. After the tutorial, the experiment was started. In the experiment, the user repeated the same task, this time for 20 times. So we constructed 2 hypotheses. The first one was that tangible interaction would improve performance. The second one was that tangible interaction would increase presence. And then we carried out a between subjects user study with 40 participants. Half of the participants tried the experiment version with the tangible ball. The other half tried the controlled version, which was purely virtual interaction. And each participant first completed the tutorial, then completed 20 trials with the assigned interaction method. And we discarded the data from the tutorial to avoid any learning effects. So here is a video showing the experiment and control versions in our user study. So if we take a look at the results for user performance, for us, user score in the game indicated their performance, and the score was out of a total of 60 for 20 trials per participant. And then the overall score per participant was calculated by summing the score values for all trials per participant. And then we conducted 2 sample t-tests for all metrics. We found out statistically significant difference in user performance based on the scores. And with the tangible interaction method, the scores were higher. For presence, participants rated the questions from the presence questionnaire on a 7-point Likert scale. And then the aggregate presence score was calculated by averaging the responses for all questions per participant. And presence scores were statistically significantly higher for the tangible interaction group. We saw no statistically significant difference in motion sickness scores for both groups. So what does our results mean? In our study, tangible interaction improved user performance significantly and supported our first hypothesis. We think that the two main reasons behind this could be the tangibility provided by the passive haptic and the kinesthetic feedback. Participants might have found guiding the direction of the ball easier with the tangible user interface since it provided haptic feedback. We also believe that the haptic feedback and the kinesthetic feedback would have made it easier for the participants to apply the correct amount of force while kicking the ball, and hence making them more successful in terms of user performance in the game. And our results also indicated that tangible interaction improved perceived presence significantly, supporting our second hypothesis. Again, we think that the main reason behind this could be the added tangibility, which would connect the virtual and physical worlds better and connecting the overall senses of the participants better with the tangible user interface. There are some limitations to our study, of course. Our setup was room scale, task design was impulse controlled and not position controlled. We used real world physics and for the tangible ball, and we approximated that in the Unity game engines using its physics engine for the virtual ball. And then we didn't measure perceived fun, and also we used a wired headset. Possible future work directions would be exploring foot-enabled interaction in VR with objects of different forms or sizes, and then including hands and feet in tangible user interfaces in VR, and finally measuring hedonic quality through perceived fun or joy. This concludes my presentation. Thank you very much for listening.
Excellent. Thank you, Lila. Okay, so our next speaker is Jason Woodworth from the University of Louisiana at Lafayette. He will be presenting redirecting desktop interface input to animate cross-reality avatars.
Sure thing. I'll share my screen. Right. Are you able to see it now?
Yes.
Okay, great. So, like you said, my name is Jason Woodworth. I'm going to be talking about our paper on redirecting desktop inputs to animate cross-reality avatars. I'm presenting on behalf of my co-authors. We are all from the University of Louisiana at Lafayette. So, okay. So our goal here is to address a current gap in the current quality of VR and desktop-driven avatars. We find that desktop-driven avatars in cross-reality VR applications, such as Mozilla Hubs, or in fact, Verbella, which we're using here, the desktop avatars are significantly less expressive and less directly mirror what the user is intending to put onto their avatar. To do this, we are trying to develop a novel animation framework that redirects the user's desktop input. And to evaluate it, we developed a two-phase user study that evaluated it from the viewer's perspective. As an example for this, we look to sort of the high rates of learning loss among students who are using standard remote meeting tools like Zoom or Skype to replace their in-classroom learning. If any of us have been teaching or parents to students, it's not hard to see the effects that these tools have had on their direct learning outcomes. So we believe that some of this problem may be due to a lack of feeling present in the classroom or a lack of a sense of engagement with the teacher that these desktop or phone-based applications just don't allow for. So to try to address this, some educators and conferences like this one have turned to existing VR meeting spaces like Mozilla Hubs. For example, this is a video of a VR avatar in Mozilla Hubs. You can see that the avatar, even though it's a little robot guy, is still pretty expressive. You can see kind of how he's feeling by the way that he moves his hands, the way that he's able to move his head, etc. But the use of VR is sometimes impractical for long 7-hour teaching sessions. So some of these cross-reality environments often have a desktop interface in which they can use a desktop avatar. But as you can see from the avatar in Hubs, it's much less expressive. You just get to move around with WASD keys and mouse movement, and there's no hands or anything like that. So to address this, we created the novel desktop interface, which uses some additional sensors, such as the Leap motion hand tracker and a Tobii eye tracking bar. And these redirect users' 2D input from the desktop through a what we call redirection layer using redirection modules that'll redirect things like users' eye gaze or their intended pointing motion or their hand tracking, bring those through a prioritization layer, which tells the avatar where each body position or body part needs to be positioned, how it needs to be rotated. And then we use a body mechanics layer, which drives the body part to that given position. So what does all of that look like? Well, here we can see our what we call S-Desk, which is a desktop with sensors avatar, who's able to point around at this little board. He's able to move his gaze around the room as I move my own gaze around the computer screen. As I move my mouse and try to point on the board or draw on the board, he's able to use his hands to point at the same space based off real recorded human pose data. And we add in some hand tracking there as well, so you can use hand gestures and stuff like that. We also created a version that does not need the additional sensors, using primarily just mouse-based inputs. So the gaze will be using the mouse and it'll look towards whatever the user is currently clicking on. We did this to show the impact of these sensors and see if the avatar is still likable without them. To evaluate our methods, we wanted to compare them to some more conventional avatar styles. So we used a headset-based interface, which drove the same kind of avatar using a Vive Pro Eye. And we created basically a recreation of the Mozilla Hub's first-person desktop interface, in which you have a basic first-person controller where you move the camera around with the middle mouse click, and you can still draw on and look at the board and stuff like that. In order to compare these 4 avatar conditions, we conducted a 2-phase study with 36 subjects, in which these subjects evaluated the avatars from a student perspective. In this first phase, subjects took on the role of students watching each avatar give a short presentation, about 2 minutes, on some local bird to Louisiana. Combinations of the 4 avatar conditions, it gave a presentation on different combinations of the 4 birds, and the combinations were randomized across all participants. So, for example, one subject might watch this S-Desk avatar or the sensors-based desktop avatar give a presentation on the American goldfinch, whereas, and then also watch the VR avatar give a presentation on the northern cardinal, whereas another user might have those swapped, or some other combination of avatar and bird presentations. To evaluate these, at the end of each presentation, subjects were given 6 questions, one with a simple quiz on the presentation material, a question on how human-like the teacher was, how lively they were, and a few others which are further addressed in the paper. And we also measure the angle between their current gaze vector and the direction to the teacher's eyes. So essentially, how far away are they from the teacher are they looking? In phase 2, we wanted to get a deeper understanding on the perception of the individual motions that were created by each redirection method. And so we asked them to rank clips of each avatar performing greeting, pointing, and drawing motions, and then to rank them by preference and strangeness. So here, each of the 4 avatar conditions gives a brief, about 7 to 10 second clip, doing a greeting, pointing, or drawing motion. And then afterwards, the user provides a ranking of which recording they liked most with the ability to replay them at will. So for conclusions, we analyzed this data primarily using Friedman tests with post hoc Wilcoxon-signed rank comparisons with Ponferroni corrections. And from this, we draw 4 main conclusions. First, when we look at our question on humanity, which is the thing we're primarily interested in to start, because we assume people will want to be in a room with a teacher that they consider to be more human than robot-like. We see that the VR avatar is considered significantly more human than the conventional desktop approach, with the VR getting a 4 out of 5 on average and the conventional desktop getting a 3 out of 5. So a fairly significant difference. This goes to show that current cross-reality desktop interfaces are sort of providing a subpar or lesser quality avatar for their desktop users. Secondly, our novel interface with the sensors. Pardon? Thought somebody said something, sorry. Second, our novel interface with sensors is not found to be significantly different from either of these. But since the since the VR and CDesk avatars differ themselves, we know that it can't be equal to both of them. So looking at the average value and the p-values, we assume that it's more likely to be different from the more conventional desktop, which would place it closer to the VR avatar in terms of ranking, which we expect which we expect to be likely. We weren't intending to necessarily make something that's better than VR, just something that can get closer to it without having to have the user be fully immersed in the headset for however many hours that they're going to be teaching. Third, we see that our sensors-based avatar and the VR avatar attract significantly more eye gaze than the conventional desktop. The lower average angle for these two implies that the subject is spending more time looking at or near them, which we'd consider important for engaging a student or any other user of some kind of cross-reality VR platform. And we see moderate effect sizes when comparing the averages. Finally, results from our phase 2 show that our novel interface without sensors still is showing improved rankings when performing drawing and pointing motion. Specifically, when we look at pointing motion, we get a very clear hierarchy ranking here, with the VR being the most well-liked and the conventional desktop being the least liked, with SDesk fitting somewhere in between here. But primarily, we're interested in the idea that this non-sensors using desktop interface still has some viability for those who don't have access to the sensors or don't want to have to be using eye tracking at all times. So we thank you for attending the presentation. Hope that you'll check out the paper and enjoy what's left of the conference.
Excellent. Thank you, Jason. So our last speaker is Shaoyu Chen from New York University. He will be presenting UrbanRama, Navigating Cities in Virtual Reality.
Yeah, thanks for the introduction. Can you see my screen?
Yes.
Okay, so hi everyone. Today I will present our work, UrbanRama, Navigating Cities in Virtual Reality. Exploring larger virtual environments, such as cities, is a central task in several domains, like gaming and urban planning. VR systems can greatly help this task by providing an immersive experience. However, a common issue is with viewing and navigating a city in the traditional sense is that users can either obtain a local or a global view, but not both at the same time because of occlusion. Therefore, users have to continuously switch between perspectives, which may result in losing context and distracting them from their analysis. Collaborating with architect and urban planning experts, we would like to build a navigation system that overcomes this challenge and satisfy the following 3 requirements. The first is to provide a local as well as global perspective during the exploration process. This allows users to preserve context without having to constantly switch between different perspectives. The second is ability to quickly locate and move to building locations or points of interest. The third is to have a small number of controls. This is especially important to not overwhelm users who are not power users. To provide a local as well a global perspective and satisfy requirement 1, we apply space deformation in our method. As shown in this figure, the user is looking north, standing in the front of New York City Hall in the south of Manhattan. The symmetrical projection enables users to have a direct line of sight to 3 important landmarks in Midtown, highlighted in red. Here is the view of the user. Our method utilizes the unused sky space to provide global perspective while keeping the local context. Our method first maps the point on the ground to the surface of cylinder by connecting the points and the north pole of the cylinder. In this example, the P0 prime and P1 prime on the ground are mapped to Q0 prime and Q1 prime. This method can be extended to support 3D buildings. For a 3D point with height, we first map its projection on the ground to the surface of the cylinder. Then, the point on the cylinder surface is translated towards the axis of the cylinder by the height. In this example, the 3D point P0 is first projected to the ground and become P0 prime. Then, the map Q0 prime is translated towards the axis C by the height of P0, which results in Q0. After having the space deformation, we also need a navigation interface that allows users to navigate with the help of the space deformations in an easy and intuitive way to satisfy the requirement 2 and 3. It is the result of an iterative design process consisting of 3 main phases. We choose to use a single controller instead of both to simplify and minimize the control. We perform 2 user studies, a qualitative one and a quantitative one, to evaluate our method. For the qualitative one, there were 11 professional participants, including architects, urban planners, computation designers. They were all from a leading architect firm in New York. We designed this study to evaluate how experts perceive the usefulness of UrbanRama and to improve the interface as the last phase of the iterative design process. For the quantitative one, 30 participants were all university students. This is because we would like to evaluate UrbanRama's impact on general users, such as navigation performance, distance and orientation perception, and motion sickness. In the qualitative user study, participants were still asked to complete tasks designed to mimic potential navigation and localization use cases. However, we use a sync cloud protocol to collect feedbacks and judgments about the interface instead of objective matrix. The feedbacks from the experts were quite positive, and 10 of 11 experts agreed that UrbanRama was useful or helpful. Experts mentioned that UrbanRama was more efficient and was easier to go between places, which indicates that the requirement 2 is satisfied. Experts also appreciated that UrbanRama provided a local as well global perspective, which indicates that the requirement 1 is satisfied. In quantitative study, the participants were divided into 3 groups, and each group had 10 participants. The first group is the flat mode, which is the baseline. The second group is Rama mode. In this mode, besides the functionality in flat mode, users also have access to UrbanRama. The third group is Minimap mode. Users have additional access to a minimap near the controller. This user study consisted of 4 tasks, all evaluated by using quantitative matrix. Motion sickness was also measured using simulator sickness questionnaire at the beginning and the end of the study. The first 2 tasks were used to evaluate navigation and search performance, and completion time and time spent in different altitudes are recorded. The last 2 tasks were used to evaluate distance and orientation perception, and the numbers of errors are recorded. Here is the summary of the user study results. As shown in this chart, users spend significantly more time at G level in Rama mode, which indicates UrbanRama provides the global perspective needed to complete the task, while maintaining the local context and satisfy the requirement 1. Also, this chart shows that users spend less time to complete navigation tasks, especially for users with VR experience, which end with E in each row. The errors that users made were similar for all the 3 modes. Therefore, we believe that UrbanRama doesn't affect distance and orientation perception. Thank you for listening.
Excellent. Thank you, Shaoyu. All right, so now we're moving on to our Q&A. So we'll just jump right into it because we only have about 10 minutes left. So let's see, Guillermo, I have a question for you from the audience. This is from Kunal. In your research, did you come up with any techniques or design decisions to reduce the motion noise of the sensor data? You know, a lot of these physiological sensors, they're susceptible to motion noise when the sensors are moving around. Did you come up with any techniques to reduce that?
Yes, we have a paper coming out that looks into a lot of its features, but since for this paper, we were looking specifically at the device, the signals, and the capability. One thing that we show is that you can, by using lab stream layers, you can leverage existing toolbox. One that we have been using is NeuroPipe. NeuroPipe is free to use for people that are in academia. So if you're in academia and you wanted to try it, you can just hook up, and they have a very nice tool set that allow to remove a lot of these artifacts, blinks, gate, and others.
Excellent, excellent. Thank you for that. All right, let's see. The next question. So let's see, Shakiba, this is for you, and this comes from Rifital. Did you use any eye tracking information for understanding the user's attention or gaze in the context-aware condition?
So no, so for this study, since like the whole point of this study was just to validate the benefits that they can offer, context-aware system can offer to like users' performance and their preferences, we didn't have that, but that's actually a really good question because this is like some of the data that we would definitely need to, in order to know how to design the interface, even when we know the user's context. So for my next work, we're trying to gather some data, and potentially, most probably, eye tracking would definitely be one of those.
Excellent. All right, thank you for that response. So let's see, the next question is for Jay. There's actually quite a few questions for you, Jay, on Discord, but I'm going to jump in line here and ask you my own question. So you reported differences between the 2 studies, especially with regard to the desaturation Q. Can you talk to why you think you found those differences between the studies?
Oh, so you mean in study 1 and study 2? Is that correct?
Correct.
Okay, so so the desaturation design, just to reiterate, was basically that, you know, it takes out color from everything in the world except for your sort of destination and your path. The problem with sort of the in a sort of an image setting, this actually looked really good because what we had was like a grocery store, for example, and it was an item that had the color intact and everything else was, you know, sort of grayed out. So in that case, you know, it's really easy to find that one item. So then when it comes to finding an item, this is really easy because, well, it makes it very obvious that this is the one thing you're looking for. But then when we apply desaturation to the world and people are able to explore the world, a lot of the participants said that they lost too much real world information. So for example, they still want to be able to see the world. They still want to be able to, you know, experience the world, not just look for that one target. So in a targeted task, for example, where all you have is a target and you just need to get there as fast as possible, then in that case, desaturation is okay. But in any other cases, it might not be the best solution because it does take away too much real world experience for the users.
Great, excellent.
And
Thank
I
you for
will
that
try my
response.
best to get to all the Discord questions. I've been doing that, so.
Great, excellent. Appreciate that. Okay, let's see. So our next question is going to be for Lila. This is from Michael Bonfert. Did your control group participants share how good their perceived control over the ball was? Or did you do any type of assessment of the quality of the physics simulation?
Sure.
Those are
Great
two separate questions. So
yeah,
yeah.
I figured that. Great questions. So for the sense of control in our control group participants, in the presence questionnaire, there are questions that measure control factor, and those include questions such as how well could you move or manipulate the objects in the virtual environment, and other questions like that. And when we measure the control subfactor, specifically, there was no significant difference between the tangible and control experiment and the control groups. So we suspect there was no issues of sense of control based on this, but the overall presence was significantly different for the two groups. And in their qualitative feedback, we didn't receive any negative feedback regarding the lack of feeling of control, but they mentioned the awkwardness of not having a haptic feedback. And for example, let me see, a participant said, I would have liked to feel the response on my foot of the ball touching when I kicked it. The lack of it felt more like just touching a balloon. So we think that they felt the awkwardness of not having haptic feedback, but they didn't complain about a lack of sense of control. As for the second question, to approximate the physics behavior of the virtual ball to the tangible ball, we conducted several in-house testings. And to do that, we activated both balls in the simulation. We activated the tangible ball and the virtual ball at the same position through the software. And then we kicked the balls with the same amount of force at the same time. We applied simultaneous kicks several times, and then we adjusted the behavior until we got a really close behavior of the two balls, both the tangible and the virtual. And we adjusted the physics values in Unity accordingly.
That's a great approach. Very intelligent. Real quick follow up on the lack of haptics from the participant point of view. Have you considered looking into pseudo haptics, where you visually basically kind of delay the movement of the ball until the user's foot moves a little bit further, so that they get a sense of force or feedback from the ball itself?
Sure, I think that's a great future work direction. For this study, we tried to be, since there are not many foot-based interaction with tangible user interfaces in VR, for this study, we tried to be as similar as possible, but I think that would make a great future work also area to look into. Great,
excellent. Well, thank you so much for those responses.
Of course, thank you.
Thank you. All right, so next up, Jason, I've got a question for you. So, in your study, kind of the summary or conclusion I got from the study was that HMD is really kind of best for this perception of these virtual humans. Out of curiosity, did you consider looking at a condition where the user had two handheld VR controllers, but they didn't use the head-mounted display, so it wasn't immersive, it was still kind of desktop-based, as opposed to your sensor setup?
I believe at some point we had considered that, but the practical, because we wanted to develop it for sort of a teaching-based system, the practicality of having to put the controllers down and then having the model just have its hands go off somewhere while the person types at the keyboard or moves their mouse to access files and things. It seemed a little impractical. It's something that we could definitely use if targeting other more generalized applications. And that might be interesting, especially as things like head tracking from something like the Tobii eye tracker or a Kinect or anything like that gets more advanced. So the user can maintain that sense of comfort while getting more fidelity with their animation.
Great, excellent. Well, thank you for that. And then let's see, we also have several questions for Shaoyu. Let's see, let's jump in here. I have a question from Steve Feiner. He says, based on his very quick browse of your paper, there seems to be some interesting differences relative to Lorenz et al.'s pedestrian view. What made you to decide on your approach?
I think I will need to check what is the pedestrian view for, and then I can answer this question.
Well, maybe I can give you an alternative question because we are short on time. Okay. Have you seen the movie Inception, and did it influence? Was that kind of the inspiration for your work?
Yeah, I think we mentioned this in the paper.
Okay, all right, excellent. Well, thank you very much. So I think that we're about to wrap up. We just have 1 minute left, so I'm not going to go over time. I prefer to stay on time. I would like to thank all of our speakers for showing up and giving us their wonderful presentations. And I hope that everyone in the audience enjoyed this this last session, this last talk session, and try to enjoy the last couple events of the conference. Okay, thank you all.